Hello, guys. So this is a continuation of our lecture on power series. We want to continue with Taylor series and the Taylor polynomial. Actually, Taylor and Maclaurin series, and then the Taylor polynomial. So here, what we want to do is that we want to be able to represent functions as power series as before, but now we want to be able to determine, right? Remember that we defined a power series to be a series of the form, let's say f of x is equal to sum Cn, say x minus a raised to the power n. Okay. If we knew what the Cn's are, right, then we have the power series. Okay. So there's a theorem that helps us to find what the Cn's are. And so by using that theorem, we know Cn's, we put it back in there, and what we get is what is called a Taylor series. Okay. So that is what we're going to do next. So the goal is to determine also which functions can actually be represented as a power series. Okay. So that's one of the other goals. In other words, given a function, if I'm able to write it out as a series, does the series that I have actually represent the function that is given to me? Okay, if I add the terms of the series, does it approach, right, the function within the radius of interval, within the interval of convergence? So we'll look at that later on. But here, this theorem says that if f has a power series representation at a point A, in other words, if f of x can be written as this, okay, within some interval of convergence, then the coefficients, these Cn's here, are given by this expression, okay? In other words, you can relate the coefficients to the derivatives. F to the n here are the derivatives of the function. So you can actually relate these coefficients here to the derivatives of the function that you have. Okay, so that is the power index. So if I just plug this guy here back into Cn, I get a Taylor series. That is basically the Taylor series. So a Taylor series is basically given by the power series, but now the coefficients are given by the derivatives of the function divided by n factorial here, multiplied by, this factor, this x factor that we have from before. Okay, so of course, if you just expand this, then you're going to get that the value of f at 0 at A, right, the center. Okay, you plug in when n is 0, you have this. When n is 1, you get this expression. When n is 2, you have that, and so on. Okay, so often if you want to find a Taylor series of a given function, the most work you have to do is finding these derivatives, right? You have to find the derivative at the point, at the center that you are given or that you want. So you need to find these derivatives and put them in this series, right? And then hopefully you'll be able to rewrite this series in a compact form like that. Okay, good. So that's a Taylor series. A Maclaurin series is a Taylor series where the center is 0, right? Where A is equal to 0 here. So the Maclaurin series is a series given basically by this, in this case, the A here is now 0. And so you just have x raised to the power n, okay? And that is called a Maclaurin series. So if you're asked to find a Maclaurin series, you will not be told that find a Maclaurin series at A equals 0. Once you say Maclaurin series, you know that the center is 0, okay? So you have this, of course, when you expand this out, then you're going to have this series here, okay? Similar to that. Okay, so I'm going to, I will do 2 examples, maybe 3, of how you find a Taylor series of a given function and how you find a Maclaurin series of the same function. And then another example, which I'll probably skip for you to take a look at, okay? So here is an example. Find a Taylor series representation of f of x is equal to the cosine of x at A is equal to pi. So our center now is equal to this number pi here, okay? So how do you find a Taylor series? Well, it's straightforward. Just use the definition that we have. It's given by this, where these n's are, again, the derivatives. But in this case, a has been given to us, is pi. Okay, whatever this is, that's why you put in a. So replace a with pi and you have that. So we need to expand this and find the various derivatives and put them in. If you expand this, you're going to get this, right? This goes on. It's going to infinity. So you need to find f of pi. F is cosine of theta. So you need to find f pi, f prime at pi, f prime at pi, and put everything back in here. So let's do that. If f of x is cosine of x, if I put pi there, I'm going to have cosine of pi, which is just -1. Then I need to find f prime, right? I need to find f prime. The derivative of f is negative sign, and then put f prime at pi. Negative sign of pi is 0. Then find the derivative of this, right? 5 prime with the derivative of negative this, that will give you negative cosine of x. Find pi of that. Because pi cosine of pi is negative, the negative cancels this, and I have 1. Okay, so the rest follow. Find the third derivative. You have sine, that will give you 0 at pi. Find the fourth derivative. You have cosine of x, that is a -1. Okay, at pi, and then do that. Okay, so I've done several of them. These are easy to do. So f raised to the power 8 is cosine of x, and cos of pi is -1. Okay, so why do you stop? Well, you do as many as you can until when you put it back into the series, you begin to see a pattern, right? That hopefully helps you to put everything back together as a series under this summation symbol. Okay, so that is what happens here. Here I'm doing more because you see some of the terms are canceling. So you have to do more to see how the pattern evolves. Okay, good. So now that you have this derivatives at the center pi giving you, you go back and put everything back in here. Okay, put everything back here. So wherever I see f of pi, I'm going to put -1. When I see f prime of pi is a 0. Now notice that the odd powered terms are all 0, right? Where x minus pi is raised to the power an odd number, like 1 here. Those terms go to 0. So this guy goes to 0, this guy goes to 0, the other odd ones goes to 0. And what you are left with are the even ones, okay? So put all of that back in here. And when you do, you're going to have this. You're going to have this expression. The first one is a -1 plus 1 over 2 factorial x minus pi squared, and so on. The odd ones go to 0 and just have these even ones. So you see, because we have these long ones, it helps us to be able to see a pattern and to write it in a more compact form. Okay, so I can rewrite this. Note that I have a negative, a positive, a negative, a positive. So that is why I have this here, -1 to the n plus 1. And because I'm starting from n equals 0, right, that will give me the first one to be -1. Okay, and also see I have 2 factorial, 4 factorial, 6 factorial. So I can write that as 2n factorial, you see? And the same power is up here. 2, 4, 6, 8, so I can have 2n up here as well. So this is how so this is the Taylor series representation of cosine of x at a equals pi when the center is pi, okay? So that is what you get when you want to find the Taylor series. Good. Now, so you may want to do this yourself, right? Just try this yourself and make sure you get what is in here. The second example says, find the Maclaurin series representation of f of x is equal to cosine of x. Okay. So as I said before, once you see Maclaurin series, it means that the center is 0. So nobody says, will tell you that the center is 0. So you have to know that you have to find the derivative at 0. So when you do, basically similar to what we've done before, in this case, a is 0. So I'm going to have this series here. I replace a with 0. A is 0, so I just have x to the n all over n factorial here. All right, the a is 0. So I need to find the derivatives of the function at 0 in this case. The other one was at pi, okay? And if you expand this, this is what you have. So you find all the different derivatives and put them back in this, okay? And once again, try to see if you can rewrite it under the summation. Okay, so the same derivatives because the same function, but now when cosine of 0 is 1, it's no longer negative 1 at pi, right? So you have 1 here, you have 0, you have negative 1, 0, you have 1, 0, negative 1, 0, 1, and so on. Okay, so you take all these numbers, right, and put them back into this series. When you do, again, the odd terms, because it's still the same function cosine, the odd terms are going to 0, right? And the even terms are remaining. If you put them back, you're going to get this series here. So basically, this is the series. But because there's a repeating pattern, we can write it in the nice form. We can write this as negative 1 to the n all over 2n factorial x raised to the power 2n. And when you put n equals 0, n equals 1, you begin to get these terms. All right, you can always test. You can always put this back and make sure that this is you get back the series. Okay, so that is how you find Taylor series, and that is how you find a Maclaurin series. Okay, it's quite straightforward. Most of the work is in how you find the derivatives at the point. That is the work involved in there. Here's an example. I will let you look at it. You want to find the Maclaurin series for the function f of x is equal to e to the x. In this case, it's quite simple because all the derivatives will give you e to the x. So because a Maclaurin series, e to the x at 0, of course, will just be 1. All right, e to the 0 is equal to 1. So all the coefficients, the derivatives, I should say, right, at 0 will be 1. All of them will be 1. So if you put everything together, you're going to get this series here. So e to the x is actually x to the n all by n factorial. Okay, so it's straightforward. You can try it. Good. So that is it about how you find the Taylor series and also how you find the Maclaurin series. Okay, that's how you compute them. Good. Now we want to move to a phase which is a bit more at a deeper level at if you like. That is because now we are asking a very critical question that if I have a function, for instance, cosine of x, and I'm able to write it as a power series, okay, as a Taylor series or Maclaurin series, what shows that if I keep adding the terms of this series that I have, I'm actually convergent to cosine of x or sine x to the function, okay? So does the series actually represent the function? So we'll look at some theorems. I'll state them, but before I state it, I'll preempt it with some explanation of how you can prove it. Okay, good. So now let's start with this. So this is an important question that is there, right? We want to look at the nth degree Taylor polynomial. I'll explain what that is here. So question is, under what circumstances can we really say that a function f of x is equal to the sum of its Taylor series? So that's what I just said. Suppose I have a function, I'm able to write it as this Taylor series. Does it really converge to the function f of x for which I found the series? Does it really approach it? Okay, so that is a critical question and it's important as well. Okay, good. So how do we go about to really show that the series, this infinite series here, infinite power series, actually converges or approaches this? Now, the trick here, or the method, is to remember the definition of what we mean by a series is convergent, right? We said that a series is convergent if I find partial sums of it, right? Remember, we said if I have a series an, right? N is from, let's say, 0 to infinity. Okay, this is a series. S1 is equal to the first term, that's A naught, if you like. S2 is equal to, yes, S1 will just be, okay, I have S naught, let me use S naught. And then S1 will just be A1. S2 will just be A2, sorry. Partial sum. So I'm going to have A naught plus A1. Okay, so this is a sum. A2 will be A naught plus A1 plus A2. Okay, let's say I add these guys up to the up to some n, up to n. So you go, you do this, and you get to, okay, so I'm going to come here, up to some n, as n is equal to a naught plus all the way to an. Okay, good. So this is the nth partial sum, right? Good. Now, this is not going to, this original series, remember, is going to infinity. But this partial sum, I'm only summing up to the nth term, right? We said that what we mean by that the series, the infinite series actually converges if I find the limit as n goes to infinity of this partial sum, if this thing exists as some number s, then I can conclude that this partial sum, right, this infinite sum, I should say, actually converges. That's what it means to say that an infinite series converges. You have to look for the partial sums, sum up to some number, okay? And if those partial sums as n goes to infinity, if they exist as some number, then you can conclude that the series converges. So that is the idea that is going to be used, we're going to use here, okay? So in this case, we're going to look at the power series. So here, to be able to answer the question whether the series actually represents the function, we want to show that, basically show that this series actually converges to the function. How do you do that? Well, you start with what we call the nth degree Taylor polynomial. In other words, you are going to sum, basically you are looking at the partial sums of this series. So you are summing from j equals 0 up to some n, you see, like what I just did. You are summing up to n, okay? If you expand this, you're going to get this. Good. So it means that if I find a limit as n goes to infinity of this partial sum, and it gives me some number, that number has to be the function, okay? Has to be the function. If it is, then of course, then I have shown that the series converges to the function. That is basically that question, okay? Good. So the partial sums that I just wrote down, well, you can, yeah, similar to what I just did. You can write the first sum is given by this. The second one is given by this. You are basically adding the sums. The third one is given by this. These are the partial sums. And then from definition, if the limit as n goes to infinity of this partial sums is equal to that function f of x, then the power series, right? The Taylor series actually converges to the function f of x, okay? So basically that is the idea. And so there's a theorem that actually captures this idea. So all this explanation is inching towards that theorem so that when you see it, you understand where it's coming from. Okay, now if Rn, for instance, let's call Rn the remainder of the Taylor series, right? Remember the Taylor series is summing to infinity. So I have a series n equals 0 to infinity of this Taylor series ns of x minus a raised to the power n. This is the same as I'm going to sum all the way to n, some n. Let me call it big N, okay, of this series. Okay, plus I'm going to sum to m, and then know that this is going to infinity. So I'm going to have a remainder. You see that? So that is where that remainder idea is coming from. I have a series that is going to infinity. I sum only the first up to m times, right? Then there's a remainder from m plus 1 all the way to infinity. That is what is called the remainder term. Okay, good. So now if I find a limit as n goes to infinity, this guy now is the partial sum, right? This is like our Tn that I talked about. So this is a partial sum. So remember we said that to be able to prove that the series converges to a function, the limit as n goes to infinity of this partial sum must go to f. All right. If that happens, this means that I need this guy to go to 0. Then this series will actually be converging to f as n goes to infinity. Okay. So I'm going to show that here. Here. So here. So the series which is going to infinity is equal to the partial sum plus a remainder. So I take the limit as n goes to infinity. This has no n, so it remains as f of x. This is the same thing as here. This is this. Now, go back. This is what we want. We want the limit as n goes to infinity to be equal to f of x. But look at here. We still have this guy. If this guy goes to 0, then we have what we want. We're going to have the limit of this going to f of x. So for the series to converge to the function, you want the remainder term to go to 0 as n goes to infinity. And that is what the theorem I'm going to state is talking about. Okay? Good. I hope that makes sense. You would probably have to listen to it a couple of times to grasp it. Okay. Okay. So here is a theorem that captures everything I've just explained here. It says that if f of x is equal to Tn of x plus Rn of x, where Tn is the nth degree Taylor polynomial, basically the partial sums of f at A. And if this is the case, and the limit as n goes to infinity of this remainder term is equal to 0, then within the interval of convergence, f is equal to the sum of its Taylor series on the interval. Okay? If this holds, if I can show that the remainder term as n goes to infinity is going to 0, then the series, the Taylor series, actually represents a function for which you found that series. Okay, that is this theorem here. So it's very important. So suppose this is true. The question now is that how do I really show that? Given a series, how do I show that the limit as n goes to infinity of Rn is 0? Because I need to be able to show that in order to prove that the given series actually represents the function. Okay, so there are two theorems here that helps to be able to do that. One is a Taylor inequality, and the other is a bit simpler, right, which you can actually do prove. Okay, so here is the Taylor inequality that helps you, right? It is one of the ways that helps you to actually prove that the limit, this limit as n goes to infinity of the remainder term goes to 0. Okay, this is basically to help you do that. So the Taylor inequality says that if the nth plus 1 derivative of the function f is bounded, is less than or equal to some m within the interval of convergence, then the remainder term of the Taylor series satisfies this inequality. Okay, so this is the remainder term that we want to find the limit and show that it goes to 0. That inequality is bounded by this. That remainder term is bounded by this inequality. Okay, so for the most part, what you want to find is find this m here, right? Show that the nth, if you can show that the nth plus 1 derivative is bounded, right? Is bounded by some m, then you can pick this m and put it in here and find the limit as n goes to infinity of this guy and see whether that vanishes. If that vanishes, then you can use the squeeze theorem to show that the limit as n goes to infinity of Rn goes to 0. Okay, and therefore a series actually represents the function. Now, sometimes showing that the limit as n goes to infinity of this guy is 0 requires that you use this theorem. This theorem says as n goes to infinity, x to the n over n factorial is 0. Is the same thing here. The limit as n goes to infinity of the absolute value of x to the n over n plus 1 is equal to 0. Okay? And this x could be x minus a or x minus some number, right? So you could use that over n plus 1. Okay? So what you actually want to prove is this, equation 8. But in order to be able to do that, you need to use this Taylor inequality and also this. So basically that is it. So I'll do an example to demonstrate how you do that. So here is the question. The first part is straightforward from what we've done. You can actually do it. The second bit is what I'm concerned about for now. So the first part says that show that the Maclaurin series for sine x is given by this for all x, and prove, this proof part is what we just discussed. Prove that it represents sine x for all x. Okay, so this showing part is not different from what I did for cosine of x. Okay, we've shown that. So you can do that. Find the Maclaurin series for this. So basically, you need to find the derivatives. You need to find f at 0, f prime at 0, f prime prime at 0. So you have the numbers here. You put it back in the Taylor series form, and then you have that. So I'm skipping this because we've done it for cosine, so you can easily follow that. Okay. So you have all these derivatives, put them back, and then you have this expression here, and then you try to write this expression in this form, and then you have that. So this is fine. So that is, you can do that. That is easy. The second bit is to actually show that if I'm adding the terms of this series, right, I'll actually be approaching sine x. The result will actually be approaching sine x. That is the main question. How do you prove that? Now, to prove that, the Taylor theorem and Taylor inequality will help you to do that. You want to show that the limit as n goes to infinity of the remainder term goes to 0. Okay, that is what you have to show. But as you said, first you have to be able to show that the n plus 1 derivative is bounded by some number or some expression. Okay, that is critical, because that will help you to choose this m. Once you choose this m, you put it back in here in the inequality, and then find the limit as n goes to infinity of that. That is usually the procedure. Okay, so here, the derivatives of sine x are basically sine and cosine. Is either plus or minus sine x or plus or minus cosine of x. So the n plus 1 derivative will always be one of these. But we know that the absolute value of sine or cosine will always be less than or equal to 1, which means the nth plus 1 derivative term will always be less than or equal to 1. So I can pick my m to be 1, okay, in the Taylor inequality. So you can pick m to be 1, and then you put it here. And that will give you an expression which is absolute value of x to the n plus 1 all over n plus 1 factorial. You see? So the remainder term is less than or equal to this expression here. All right? So note that if I find the limit as n goes to infinity of this expression, this goes to 0 using this theorem. Okay? So I know that this limit will go to 0, which means that the limit as n goes to infinity of the remainder term is less than or equal to 0. All right? But note that this guy, the absolute value of Rn, this guy, of course, because of the absolute value, this has to be greater than 0. All right? And then we just showed that this guy is also less than the absolute value of x to the n plus 1 all over n plus 1 factorial. So if you find the limit as n goes to infinity of both sides, we know that this guy is 0, the right-hand side. So this is 0. This is the limit as n goes to infinity of the absolute value of Rn. This guy is actually less than or equal to, this guy as n goes to infinity, we know is 0. So you see, this limit is bounded by 0 and 0 here. So by the squeeze theorem, we know that this limit of Rn has to go to 0. So by the squeeze theorem, the limit as n goes to infinity of the absolute value of Rn is 0. And we know that if the limit of the absolute value of 0, or if the absolute value of if the absolute value converges, then the series also converges, right? So if the limit as n goes to infinity of the absolute value of 0 of R is 0, then the limit as n goes to infinity of Rn is also equal to 0. So we have succeeded in proving that the remainder term is going to 0 for sine x. Therefore, the series that we found, right, actually converges to sine x. The Maclaurin series for sine x converges to sine x. That is what it means. Once you prove this, it means that this thing here, this guy here, is actually equal to, sine x, approaches sine x. As you take more, add up more and more times, you are really approaching sine x. That is the whole essence of that proof. Okay, good. You can look in some of the other texts. You will see other examples of how you do this proof. Okay, good. So I'll end the video here. We've done about 30 minutes of it. So I'll end it here, and that will be the end of the lectures on power series. Okay.